to do it. So I started giving me complicated parts. Again.
This is where we left off on this PowerPoint that basically puts everything together. So basically, the troubleshooting class will, when we finally get it into place, it's going to be a capstone course where everybody's had this. So normally this will be the PowerPoint that we'll use to start off with, where we just go back and review everything that you should already know. I think this is where we left off about what we call induction motors. Induction motors, the advantage of an induction motor is it doesn't have any brushes. It has no commutator, has no brushes. What it does is it's got a, if it's over the motor controls, I can show you this. But the rotor, and a lot of people call it a squirrel cage because that's kind of what it looks like, is it's got conductors that run like this. And then on this end, they got a shorting ring that shorts those conductors out. And then these are embedded into what we call a laminated core. So we're putting AC, but we want the current to go into these conductors. We don't want it to go into what's concentrated in the field. So if you ever look at these, you're going to see this guy right here split into thousands of individual plates that are isolated from each other. So what happens is when I put a magnetic field out here and that field expands out, it induces a voltage into that wire right there. It's shorted out, so it pulls a lot of current, which creates a real strong magnetic field, which counteracts the magnetic field of the stator and causes the thing to start spinning if it's got a phase shift. If it don't have a phase shift, then the thing will just sit there and do what? You got to hum it. It won't turn. A lot of times you can reach down and spin it, and it'll come up and eventually spin up to speed for you. Because that way, once it's rotating, then the rotor itself is creating the phase shift. Okay. Because it's shifting, and it's always lagging behind this. So what happens is we start off with a real high frequency. So what determines it? Y'all had AC? What determines the amount of voltage we induce into that wire right there? Speed of the motion. But I usually put that down. Oops, sorry. Well, my screen's bouncing. I got to put my hand on it.
You're on that heat.
Yeah, the strength of the field. And the number of conductor loops. Of course, there are certain things that you can't control. So when we start off, if I'm putting 60 cycle on this thing, then it's seeing a phase reversal 120 times a second. So that means we have a lot of what? Speed of motion. But what happens when this thing starts rotating, then we're going from 0 up to speed, and what happens is we're starting to synchronize with the field, and we're starting to lose a lot of that motion. So as the motion goes down, then the current in the rotor goes down, because it don't need all that current because it's got something at rest already in motion, right? You understand? So as the motor comes up to speed, the speed of the motion, the difference between the speed of the field and the speed of the rotor, that would be the speed of the motion between the two, which causes the current in the armature to go down. So these guys pull a real high inrush current, and then just like a DC motor, and then it drops down when it comes up to speed. Rule of thumb is what, 6 to 8 times what we call the full load current. So the nameplate of a motor does not give you the inrush current. The nameplate of a motor gives you what you call full load current, which would be the current the motor pulls when it's running at its rated voltage, at its rated frequency, under the rated load. Okay, makes sense. So once we got it spinning, we don't need the phase shift anymore, unless we want to get a higher torque when we run it. So the advantage we have on an AC motor is we don't require what? Brushes or slip rings. So it means right off the bat, that's less maintenance. That's less maintenance. That's less we got to worry requires an out-of-phase voltage to be generated in a secondary winding called the start winding. So a single-phase motor, we're going to have another winding called a start winding that we have to generate a phase shift in. And how do we generate a phase shift? We either generate it with a coil of wire or we generate it with a capacitor. Capacitors have the advantage of creating a better phase shift, which means we can get more starting torque out of it. So we have what we call capacitive motors. Some people call them capacitive start motors. And then we have what we call a split phase motor. Split phase motors use inductors to start. They don't create as much starting torque, but they're a lot cheaper. So split phase motors are going to run, a lot of your fans run on split phase motors because fans are kind of different in that they require almost no starting torque, but their torque increases with speed, right? You understand that? Split phase motors work great for fans. Starting torque is low, easy to repair and maintain. Efficiency is less than 3-phase. And then power factor is low. Y'all understand? The power factor is the difference between what we call the real power and the apparent power. Mostly used for domestic and small commercial applications, normally reversed by changing the direction of the start winding. 3-phase motors, of course, do not require start windings. Starting torque is high. These are harder to repair. They have good run torque. They have real good efficiency. They have a real nice power factor. Normally used in industrial applications. The problem is the motors are so much efficient, but the problem is getting the power to the motors is where it's so expensive. Just the wires and transformers and stuff that's required to get 3-phase. So if you had 3-phase in your house, that means out there where they got that one transformer on your telephone pole, that'd have to have what? That'd have to have 3. Instead of running 2 wires in there, that'd have to run 3. And you think about the cost on that. So it's a lot cheaper for Alabama Power to do that and then let you pay for the inefficiency of the 3-phase motor. I mean the single-phase motor. Now normally what we do in 3-phase, we call the phases ABC, or we call them L1, L2, L3. And it all depends on where you work at. Normally to reverse a 3-phase motor, we reverse A and C, or L1 and L3. And they have color codes too, by the way, red, blue, and yellow, but I can't remember which one's which. To reverse a single-phase motor, somehow we have to figure out how to switch the start winding without changing what we call the run winding. So a single-phase motor is going to have 2 windings. It's going to have a run winding, and then it's going to have another winding called the start winding. And then, of course, in series, either this guy here is going to have a lot of inductance, or he's going to have low inductance, and he's going to have a capacitor. Everybody okay?
Which is more common?
Capacitive motors are a lot more common. A lot more common. Like I say, split phase motors are relegated to devices that don't need a real high starting torque. So capacitive motor is something, so if I've got a compressor, it's going to either be a universal motor or it's going to be a capacitive motor. Because they require a lot of starting torque, right? Sometimes they'll come over here and they'll put a capacitor there. And what this does is this creates more run torque. Some people call these capacitive start capacitive run. Some of them call them capacitive run motors. And these guys create better run torque. So what's nice about a capacitive start capacitive run motor, the motor can be smaller per horsepower. But they cost a lot more money because the windings have to be done. So you'll see these used in applications where the size of the motor matters. How much space do you have to mount that motor, create your torque you'll run into. And these will have 2 capacitors out there. Or they'll have a capacitor that's got 3 legs on it like this. And you'll have one common. So we can make like one side common, right? You understand? And then this will be our 2 capacitors right there. You'll see those a lot. If you see a motor, a lot of times when your single phase motor, is they'll have a big old hump on the outside, and they'll mount, the capacitor will actually be mounted on the motor. If you ever see two of them, then that's a capacitive start, capacitive run motor. You'll see that done a lot. Most HVA systems, the capacitor will be mounted separate. This is what we're trying to do, right, to understand. So capacitive single-phase motors, what are we trying to do? Well, we're trying to create a what? A phase shift to get the thing rotating. Okay. So we have a main winding they call a what? A run winding. And then we have another winding we call a what? Start winding. Now here's a capacitive start, capacitive run motor right here. So by the way, once we get it rotating, then the start winding is no longer required because the rotor spinning creates the phase shift. Anything that's in motion wants to do what? Stay in motion. So what we can do is we can use real cheap windings in our start winding. You'll understand that. Because if we left them in there long, they would burn up, right? You understand that? So we can create a strong magnetic field with very few windings. So what we do is they have a centrifugal switch on them, and if we was over in the motor crowd, I can show you all this. So when you can hear these suckers click. So you start them up, you hear click, and what that's doing is taking out the start winding, and when it slows down, when it gets down a certain speed, you'll hear them click again, and that's putting the start winding back in. So if these things won't start, if they sit there and hum at you, then that either means this guy right here is gone bad, or this switch is gone bad. You know, I had a pump on my swimming pool that wouldn't start; it would hum. And guess what it was? Water had got in and corroded that right there. Yeah, I thought it was a start capacitor, so I carried it down to Whittington and asked if they had one, and they didn't have anyone. Thank goodness. Then I realized that I hadn't even checked the dang thing with an ohm meter. So an ohm meter, you can see these things charge and discharge. So they'll start off with almost 0 ohms, and then they'll charge up to pretty close to infinity. And so once I checked it with my ohm meter, the thing would charge fine. So I realized, then I tore the motor apart and got to start winding, and so I just cleaned it up. Are we okay? So this would be a typical single-phase motor with the start capacitor on it. Like I said, sometimes they run 2 wires. Standard color code is brown. So if you got a motor that's got 2 brown wires that come out of it, then that's for your start capacitor. And to get the right phase shift, it depends on the reaction between the start winding and the capacitor. So that means when you replace that sucker, you need to replace it with the same size. This is probably on outside air conditioning systems, HVA systems, that capacitor goes out often because it's out there in Alabama weather, right? So we've got a thunderstorm rolling in, and those will pop those capacitors. So that's why on most outside HVA systems, the capacitor is not going to be part of the motor. It's going to be mounted somewhere out there, but it's going to be 2 brown wires, right? You understand that? It'll take you over. More expensive than split phase motors. More starting torque, 2 to 400% of the full load current. Low starting current, lowest starting current. Workhorse of general purpose industrial and residential motors. In fact, from what I understand, U.S. Steel, when they were setting up the pipe mill, instead of trying to put one motor that ran everything, they put single-phase motors on every row. And then they run them with variable speed drives, which is pretty neat.
We had a few DC motors in Cuba. You know, I mean,
yeah, variable speed AC drives they're predominant now over DC motors. But if you get any older applications, you're going to run into those. And that's what surprised me about the wound rotor motor. Characteristics, this is a split phase motor, less expensive than a capacitor motor. They're very low horsepower, very low starting torque, 100 to, so the other one is what? It's 2 to 400. This is 100 to 175. High starting current, so these guys take a lot more current to get it started. Of course, they run off single phase motors. Some of your grinders use this. If you ever have a grinder, you turn it on, and it takes a little while to get up to speed. That's split phase motor. because it can't create all that starting torque.
I
If
had
that-
one, I had to run across the table to get it started.
Well, then that's definitely. Well, that might have been your start winding was messed up, or your start.
It ran like a champ once it got running, but
Small fans and blowers. So these guys are predominant in fans. We use them a lot of them in fans. A shaded pole motor. I've got one of these somewhere. What they do is, I need to go find that. What they do is they take a coil and put it around one of the poles. So what you'll have is your magnetic stator, and then it'll have a groove in it out here. And then around that groove, it'll have a chunk of wire. Now what happens is when AC comes into this, it induces a voltage into that coil, and it's opposite of the voltage applied. So what it does is creates a little tiny phase shift between this portion and that little edge right there. This causes the motor to do what? Rotate. This is called shaded pole motors. We could go over there and take our pencil sharpener apart over there. That electric pencil sharpener is going to have a shaded pole motor. A lot of your little small fans use shaded pole motors. Old electrical clocks use shaded pole motor. You have to set the time on them all the time. The only problem to reverse these, the only way to reverse these is to change this guy right here. So you literally have to take the pole off and spin it around and put it in. We were over in Japan, and we had a clock. We said, I'm not going to tell you everything about the clock, but anyway, we put the numbers on backwards, and we pulled the shaded pole and put it on, so our clock at our shop run backwards. It confused people. It was so fun. So, yeah. When you understand a few things, you can do a lot of cute things too. But yeah, so we had a clock that run backwards, but it was a shaded pole motor, and normally the shade is and you can actually see the plates in here. Can y'all see them kind of? Yeah. These things are pretty easy to take apart. You could take the rotor out and just put it in the other side, and that would give you the same thing.
so the whole actually feeds all the way through?
Huh?
The whole actually feeds all the way through?
I don't know what you mean.
Well, you said you could just flip that plate around.
Yeah, because anytime we come up here and put a rotor, it's got to be within the field. Okay, and if it's a rotor, it means we got to have some type of bearing or something on both sides. So the field comes in and encapsulates the whole thing. So you can see this right here. So that's the back right there. And it's basically this, but it would be the other side of this. Most of these use sleeve bearings. They're either unlubricated, which means they're going to be Teflon. They'll be Teflon bearings, or you'll need to put a little drop of oil in there every once in a while. So we okay? Yeah, but you can see the screws. So sometimes what you do is just break this loose and then insert it into the other side, and then it would turn the opposite direction. Okay, now let's take a break, guys. AC motor tries to run at, first of all, we don't change the speed of an AC motor by changing the voltage to it. So on a DC motor, that's what we do. We either leave the field alone and change the voltage going to the armature, which changes the current. And that's the normal way to control the DC motor. So normally we use the field to control the torque on the DC motor, and we use the armature to control the speed. AC motors, if you reduce the voltage to it, then one thing's going to happen is, you remember, power varies with the square of the voltage, the square of the current. So as soon as you try to slow it down with voltage, it don't create its horsepower anymore, and what would it do? It would stall. If you put too much voltage on it, it would create a lot more starting torque than what it's supposed to start. It'd take a lot more running torque, and it wouldn't run any faster than what it's rated at. So you could slow it down by lowering the voltage, but that's very, very dangerous. Why? Because if it's a 5 horsepower motor, as soon as you drop that voltage any, power is going to vary with the square of the voltage, right? You understand? So that all of a sudden it's not creating, you drop it down to 1/2 and it's creating 1/4 of the power, then it's going to stall on you. If it stalls on you, it's going to burn up. But once you get up to its running speed, if you increase the voltage above that, you're not going to change the speed at all. So what we're saying is that a AC motor wants to run slightly less than, this is the RPM of the field, 120 times the frequency divided by the number of poles, the number of magnetic poles. Or some people teaches it RPM would be equal to 60 times the frequency divided by the number of pole pairs. And you have to understand poles come in pairs anyway, right? You can't have a north with a without a south. But most people when they talk about motors, they don't say pole pairs. They say it's a 2-pole motor, it's a 4-pole motor, and poles have to go. So this is the most popular formula right here. Now what happens is your rotor is going to run slightly less than this, because if it tried to run at the same speed, you'd get no induced voltage. If you got no induced voltage, you don't get any torque. And we refer to this as slip. So if I've got a 2-pole motor, would try to run at 3,600 RPM. But when you look at the faceplate, it's going to be like 35-25, because that's the slip, right? Y'all understand that? So how do we control the speed? If I don't control it with voltage, because once I got up to my full voltage, if I increase the voltage, the motor wouldn't do anything. If you lower the voltage, then you're varying the horsepower of the motor. Y'all understand that? A DC motor just pulls more current. So a DC motor, you put less voltage on it, the rotor's going to slow down. If the rotor slows down, it's going to pull more current and it's going to maintain the torque, right? You understand? So a DC motor, if it's 50 horsepower, it'll pull 50 horsepower whether you're running it, 100 RPM or you're running 1,000 RPM. An AC motor, we can't do that. If we lower the voltage, on an induction motor, then we reduce the amount of current we induce into the rotor. The motor don't produce the horsepower, and the motor stops. So here's our formula. How would we change the speed? We could do one of two things. So when I go up there, I've got a ceiling fan at my house, and I've got a little switch. I go click, click, click. It runs at 3 different speeds. What am I changing? How am I changing the speed? It's got to be this formula right there, guys. It's going to try to run at 120 times the frequency divided by the number of poles. 120 is a constant, so I don't change the 120. Right? You understand? Right? You understand? So I either got to change the what? Frequency or the pole. So what are you doing on your ceiling fan when you click through those 3 different? You're changing the number of poles. That's what you're doing. You're changing the number of poles. If you raise the number of poles, it speeds down. If you lower the number of poles, it speeds up. So that's a 3-speed fan, and that's what you're doing. If you looked at that switch, it's got 3 wires coming out. It's got 4 wires. 1 comes in, 3 comes out. What you're doing is you're switching between the number of poles. That's exactly what you're doing. So most of your HVA system motors will have multiple wires coming out of them. They call 3-speed fans, but you're changing the number of poles, right? You'll understand that, depending on which one of those wires y'all use. Everybody okay? Y'all understand that? But if I've got just a regular motor, how am I going to change the speed? So we're just talking about these motors out there, but we don't want it to move in steps. We want to be able to vary the speed. So US Steel's got all those rollers out there, and they want to get all of them running at the same speed. And us trying to switch between 3 speeds, that would be basically impossible, right? You understand? So we want to vary the speed over a long range. So what are we doing? We're not changing the number of poles. We got to change the what? Frequency. Well, the problem with changing with frequency is we have this big formula right here. So that means if I raise the frequency, the opposition of the motor goes up, and now it don't create the torque. If I lower the frequency, the opposition of the motor goes down, it pulls a lot more current, creates too much torque. So the actual torque would vary with frequency. We don't want it to do that. So what do we need to do? Well, what they do is they set up what they call a voltage per hertz. So if it's a 120 volt motor and it runs at 60 hertz, that means if I can maintain 2 volts per hertz, then we can change the speed of the motor. Y'all understand that? Which is pretty neat. So, and that's what you do when you program your variable speed drive, is that's one of the things you enter. You enter all that information that's off the faceplate. So it means on this one, if I wanted it to run, and it's a 2-pole motor, the maximum it would run would be something less than 3,600. Right, you understand? If I half the frequency, and I drop down to 30 cycles, and I half the voltage down to 60 volts, then that sucker will run fine. Because I'm maintaining what we call a volt per hertz, right? You understand? So if I raise my voltage and my frequency at exactly the same ratio, we can control a AC motor over a wide range of speeds. And that's what a variable speed AC drive does. Some people call it variable frequency drives. That is not correct. They are variable speed drives. Because all if they did, they couldn't control the speed with just doing the frequency, right? You understand that? So how do we control the speed of a DC motor? Just change the voltage on the armature. That's all we do. And it does whatever torque's required. It'll slow down enough to create work. Because if the rotor slows down, the resistance of the rotor goes down, pulls more current, creates more torque, right? You understand that? So it maintains a constant torque. AC motors, we can't do that unless we got a wound rotor motor. All right. So a wound rotor motor, what you do is you change the resistance of the rotor. So if you raise the resistance, it's got to slow down to induce that voltage to create the torque. And if you decrease the resistance, it speeds up.
So the reason they do that is on the door carriers, they pretty much stay all upstairs. And like they go down a decline, get the doors put on it, and they go up the next line, and they go down another decline. That's the reason they go there.
Yeah, but I just don't understand why they just use the regular AC motor with a variable speed drive on it. Normally, if they put SCRs in there, they're firing the SCRs to change the direction, and you still have an electronic circuit.
Mercedes typically was about.
Well, wound rotor motors cost a lot of money. They're on the scale of DC motors because the rotor is wound. The rotor actually is wound.
I think it's July they're supposed to change all
So the way we would change the direction of a DC motor, we have several options. As we come over here, and we put our DC motor right here. And normally this is the symbol for the armature, or what some people call the rotor. And then we do it one of two ways. We can use regular single pole relays. And what we would do, if we don't have two polarities, it would come and do it like this. And then this would be DC, and this right here might be plus, and this might be minus. And what we would do, we call this forward, and this right here would be, we call this forward, and this down here would be forward. We call this reverse, and this over here would be reverse. So that means if we close our forward, then current flow would be through this direction. If we open the forward and close the reverse, then the current flow would be that direction. So this is very popular. I think what they're doing over here on the Amatro line is they're using single pole double throw switches. So what they do is they have two relays, and they're single pole double throw, and then the armature is right here. And of course this one would start off in that direction right there. And of course, one of them would be called, they're calling K1 and K2, but it doesn't make any difference, something like that. So right now, if this is minus, then the current flow would be this direction. If I de-energize K2 and energize K1, then what's going to happen? It's going to flow that direction. So this is what I think they're using on the Amatro line. And I saw the schematic somewhere, but I can't remember what it is. It's not on the PLC print. I think all they do on the PLC print is draw the K1 and the K2, but they don't show you the wiring of the motor, if I remember.
So is that two separate switches or
They're not switches, they're relays.
relays?
Yeah, so here's our relays. So we have two relays. So that's why over there on the carriage you had to do what? You push one relay down and make it go one direction. You push the other relay and make it go. So that's probably wired like this. And you never push them in at the same time. If you push them in at the same time, then you have a great short between plus and minus. And that's one thing you got to realize about forcing relays. You need to understand the circuit that relay works within, because you can definitely cause bad problems by overriding the control circuit. So since we have two relays, you push one this in and push one that one in. This would work too. So what you do is you just change no, that wouldn't work. We'd have to push both of them in on
That's what
this.
I'm saying. Would they be mechanically interlocked?
Well, not really. If you push this one in, you'll make this, you would change the direction of this contact, but you wouldn't change that one. Yeah, so that one. No, they're not mechanically interlocked. They're usually electrically interlocked. So normally what you do in the control circuit is, it's not a light. Is what you do normally in the control circuit. Yeah, if you look at those relays, those are not mechanically interlocked. What we would do is your forward would have a reverse contact in it, and then your reverse would have a forward contact in it. So that way, if you force them at the same time with that mechanical relay, if it's wired correctly, if you force this one, you're going to open that contact. If you force both of them, then you're going to open both these contacts, and you don't have, it would appear that you have no problem, but these guys right here are still going to make it break. It's just that you cannot electrically push these in.
That's the reason I was wondering, because I was sitting there with my mind picturing, turn one without doing the other.
Now, most of your big horsepower reversers would have a mechanical interlock between the two, but you don't see that often on PLCs. And we still have the ability to force.
Even at the safeguard?
I don't know. You need to look and see on some of y'all. I know y'all have forward and reversers out there, especially on stuff that comes in and comes back out. And they'll go in and see if they have mechanical interlocks on their relays. And you can get them too. And they come as one unit, of course, because the mechanical interlock's got to be there.
Right.
And we've got one over in motor control because we don't. The reversers, we just use two regular relays to reverse. Now, what we do on AC, it gets more complicated, is that somehow we got to change the direction of the start winding. The start winding without changing the run winding or shift the other two phases. The control circuit is pretty much well the same. Normally we have two relays. One of them we call forward, one of them we call reverse, and then you use these contacts to switch the fields, right? Does that make sense? So these are called, of course, this right here is set up to what? Sync or source? Yeah, sync. You understand that? Yes. And of course, here's the one. Yeah, so here's the control device. The PLCs are set up like this. So they'll source. So they'll usually set up right here, and we'll get our output right there, right? That makes sense. Or they could use a PNP transistor, and they would be set up like this. where this would be your flush right there, and this right here would be your outlet.
I noticed that the best I use the EMPN.
Well, that's probably the sensors. That's not the sourcing or the syncing of the PLC. So normally, this is normal setup. The inputs are normally set up to sync. So they supply a comm. And then over here, our push button has to come over here and supply the power. So that means this would be what? Sourcing. But the input would be what? Syncing. Now, that don't mean it's true. So what we want to do is, I forgot. I think is it PNP is syncing. You can wire them different ways. You know, we have an induction sensor. The hall is set up like this. So inside the sensor over there, it's got common inside the sensor. But I'm hooking this up to a syncing input. So guys, how would I do that? Well, this guy right here comes out. So this comes out. So here's our sensor right here. Here's our Hall effect sensor. We come up here and we put a resistor right here. Hook it right there. And then we hook this up to 24 volts. And now when the transistor turns on, it puts a 0. When the transistor turns off, it puts a 1. And then, of course, inside your PLC program, you could change this a examinative close to the examinative open to compensate for that, right? That makes sense? Y'all all hit PLCs. Are we okay? So a sourcing sensor usually uses a PNP, which would be this guy. And a syncing sensor usually uses an NPN, which would be this guy. That makes sense. So I don't know what the sensors are over there, but we could look it up. But I think the Siemens, we can't change the inputs from syncing to sourcing. So I'm almost sure Siemens PLCs uses syncing inputs and use sourcing of it, yeah. Which is pretty standard even for most PLCs. So y'all got any questions on what we've talked about today? So we got through our motors. By the way, and I didn't put any three-phase on here. Three-phase motors, we have two types of three-phase motors. We have what we call delta motors and Y motors. And that depends on how the windings are hooked up on the inside. If you're running a single motor, if you're running a single voltage motor, it makes no difference if you're running them delta or Y. Or even if you're running a multi-voltage motor, it makes no difference if you run delta Y. Because one of them uses less coil current, but it uses a higher voltage. The other one uses a lower voltage, but a higher current. And power is equal to what? Three-phase power is equal to what? Anybody know? V times I times the square root of 3. So that means if we use a little more current and a little less voltage, we come up and get the same answer, right? You understand? If we come up and use a little less voltage and a little more current, a little more voltage and a little less current, it means we get the same power. So a delta motor or a Y motor has absolutely no difference. It's up to a preference. So a Y motor is, we usually draw it like a Y, like this. And then a delta motor is usually drawn like this. These are coils, by the way. They're not resistors. Now, what happens is when we have a delta Y motor. So a delta Y motor, we start at Y because it creates less torque. We have some big motors that if we turn those suckers loose when we started them suckers up, they would rip things apart. So you got a 600 horsepower motor, and it's going to create 6 to 8 times that starting torque. That could tear stuff apart. So normally we have two ways we can do this. We can run what we call a reduced voltage starter. So that's the problem on an AC motor. If you reduce the voltage, you reduce the torque. So what they'll do is they'll lower the voltage to start it, and then when it starts coming up to speed, they'll switch it over to full voltage. Or we can do the same thing with a delta motor. So if we start at delta, we get less current into the coils. If we get less current into the coils, we create less torque. So what we do is they'll start at delta and then they'll switch it to Y. Now this gets very complicated because you get a bunch of leads coming out of the motor. A dual voltage delta Y load motor would have 12 leads coming out of it. And we're not going to get into how to wire those.
Mm-hmm.
A dual voltage 3-phase motor will have 9 leads coming out. And it'll show you on the faceplate how to wire them for low voltage and high voltage. And remember, you need to wire it for the voltage that the motor runs on, right? You understand that? So a delta Y motor, we don't have to have a reduced voltage starter. So those are real popular in those applications. But it's pretty complicated switching those. So if it's a dual voltage delta Y motor, it's going to have 12 leads.
But they're not very common anymore.
Well, yeah, they are, especially in older applications. So you got to understand, you get into an industrial application, you get into a plant that's brand new, everything's going to be new. If you get into a plant that's been around for a while, you're going to run into all kinds of stuff.
Well, and that's what I'm saying. US Steel, you run into a lot of these newer plants that's being built with the creation of starters.
Well, what they do is they have variable speed drives, and variable speed drives can do a lot for you. They can substitute and give you a reduced voltage starter. So what we can do on a variable speed drive is we can set the ramp up. So instead of throwing full voltage across that motor, we can actually cause that motor to ramp.
Right.
We create the ramp. How long do we want to take it to come up to full speed? That's what they're doing.
Even US Steel is starting to get motor starters.
So variable speed drives are a lot more complicated than people think they are. But what they've done is basically did away with these expensive motors like this. Now we don't have to have special start motors. We don't have to have reduced voltage starters because our variable speed drive does that for us. If you're going to control the speed of a motor, you're going to require a drive anyway, even in DC motors. So a DC motor, we have big SCR drives that feeds the DC. We go to AC, we want to control the speed of the motor. We're going to have a drive anyway, but the AC motor is just so much cheaper. So and the drives are about the same price. So that's why everybody's going to every new application you see very many DC motors anymore. You see single phase or 3-phase motors, and you see variable speed drives on them. But they're not only variable speed, they can vary the torque, right? You understand that. So they substitute for reduced voltage starters, they substitute for delta Y motors, they take the place, and then of course we can control the speed of the motor with a drive, and then the motors are so much cheaper. So yeah, variable speed drives are dominating. I'm trying to get some guys, they won't do y'all any good. Yeah, I showed y'all that motor. Y'all had motor control. And I showed y'all the variable speed drive. Yeah, I did. You had that motor control. You'll see them.
I'll tell you in a minute time too.
Yeah, we'll show y'all a variable speed drive. We got one that was donated to us, but we're trying to get more. But it probably won't be in the motor controls class. It'll probably be in the motors class, which is available in the ILT, but it's one of the electives.
The motor class, which one is that?
ACDC machine. Yeah. That's where they teach transformers in more detail, and they teach DC motors in more detail than 3-phase motors. Single phase. Huh?
Who teaches that?
That's Sanders teaching.